Okay, welcome back. Now in my last video we talked about the determinant of a 2D matrix representing the area of a parallelogram formed by the two vectors that could be shown as part of this matrix. Now, as part of that discussion, we came across this value here, which was the projection of vector 2 onto vector 1. We wanted to know the value of that vector there. And what we discovered was it was v2.v1 over v1 dotted with itself. This gives us a scalar, which will be multiplied by vector 1, the vector we were projecting onto. So what I want to do today is look at where this comes from. Okay, so what I've done is a quick diagram here of vector A being projected onto vector B, or how much of vector A travels in the direction of B. That's what you can think of that as meaning. So it's very closely aligned to the dot product of A and B, but let's see what we want to find out is the value of vector U. Okay, that's the amount of A projected onto B. So U is a vector, and just thinking about vectors more in general, we've got vector U. I mean, what is a vector? It's a magnitude and a direction. So I want to know the magnitude of U, and I want to multiply it by the unit vector, which I'm going to call U hat, which has a magnitude of 1 and gives us an indication of direction. So we've got magnitude and direction. That's exactly what a vector is. Now let's look at this angle here, theta. I can see by using the cosine rule it's going to link what would be a hypotenuse formed by this right angle triangle. It's going to link, or the cosine of theta will link the magnitude of A and the magnitude of U. And that's exactly what I've written here. Cosine theta equals adjacent over hypotenuse, which is the magnitude of U divided by the magnitude of A. So that's good. But we also know we can combine this with the dot product rule, where the cosine of the angle will be A dot B over the magnitude of A times the magnitude of B. Okay, so I can end up with this situation here where this part equals that part. And I can rearrange this and do some cancelling, and we can get an equation in terms of the magnitude of U. So that's what I've done here. I can see this A will cancel with that A. These two magnitudes will cancel. And I end up with the magnitude of U equals A dot B divided by the magnitude of B. Okay, so that's great. We've got that part now already in terms of A and B. Now the next bit I want to look at is U hat, or the unit vector of U. Now if I look on my diagram, I've got the B vector, and I've got U as parallel to B. So if I had a unit vector of B, that would also be the unit vector of U. Okay, and that's what I've written down here. U hat is equal to B hat because they're parallel vectors. And what would B hat be? Well, it's 1 over the magnitude times the vector. Okay, that's the definition of the unit vector for B. And I now have U hat. So I've got the magnitude of U, and I've got the unit vector of U. And I can now combine these two parts together. So I'm going to put this multiplied by that, or down here I've written it, this times this. Now I'm going to have a magnitude of B squared on the bottom, and I'm going to have A dot B on the top, and all that multiplied by vector B. So that's here. And there's one last thing I can think about is if I do vector B dotted with itself, that equals the magnitude of B squared. Okay, so I can rewrite the whole thing again as A dot B over B dot B, and that will give me a scalar. That's just a number divided by a number. All this will give me a big number, which is a scalar for the vector B. Okay, so the projection of U will be some multiple of B. Yeah, and that's it. That's exactly what we got used in the last video. So that's an idea of where this came from. I didn't just pull it out my ass. it can be derived from this little procedure here. Okay, so thanks for watching. See you later.